But we are starting at the basics, right? We are starting with using a table to calculate the value of Kc. Now the table essentially is to get to the concentrations of your substituents or constituents of the system at equilibrium. Okay, it says look at the board now to see how to set up the table for calculating Kc. I don't have a board. And here's a few guidelines. The first one is when we set up this table, right, the formula used to calculate equilibrium constant contains the values of concentrations of reactants and products for a system at equilibrium. It says do not use any other concentration values except the values at equilibrium. Okay, so what I'm saying is you cannot substitute any concentrations in your formula unless those concentrations occur at equilibrium. That's the first thing we need to note. The second thing is we will learn how to set up our table correctly first, and if your table is set up easily, it makes life much easier. The second thing you must note is that the table must be in moles. It must be in moles. Now, if your table is not given in moles, which will be examples that I will show you hopefully later on, then you must use your mass mole calculation knowledge in order to do the conversions to get from grams or kilograms or whatever else is given to turn it into moles, okay? And that's the important thing over there. The table must be in moles. Now, what is this table I speak of? I'm going to show you that exactly now. For some of you guys, you may have done stoichiometry in grade 10 or even grade 9, so it's not necessarily just prior knowledge from grade 11. Okay, so let's just clear this and let's just see what happens in this case. Now, the best way to learn how to set up our table is to do it by the use of an example, and that's what I'm going to do with you. Okay, so here's our example. I'm just going to edit this so that we get a little bit more space over here to calculate this. And so typically these are what the questions would look like, right? It says hydrogen and iodine gas react according to the following equation. The equation is given. Everything is in the gaseous phase, so you can clearly see that setting up the equilibrium constant here should be fairly simple. Kc will equal to Hi, and by now you can see we're doing a lot of just writing out the formulae, because you get a mark for this, by the way. You get 1 mark for writing down this formula correctly, and that's 0.6666 recurring percent in a matric examination. Okay, divided by H2 multiplied by I2. Okay, both of these are raised to the power of 1. Okay, now I'm going to teach you how to set up a table. Now, some people call it a rice table. You could call it rice, you could call it ice. I'm going to show you how we do this exactly, right? Let's start with number 1, step 1. Number 1 is you write down the equation. So I'm going to write down the equation here on top. It's H2 in the gaseous phase plus I2, and that gives me a reversible reaction. It gives me 2Hi, right? Which I'm just going to put there as Hi. And then I'm going to put this in blue just so that we can see that that's 1, and that's 1, and that's going to be 2, because those numbers are going to become incredibly important in a moment. Okay, so step 1 is to write down the equation. That is step 1. I'm going to list it there, step 1. Step 2 is to draw a table, and I'll show you how to draw a table. You simply get some lines or a ruler or whatever you want to use, and you draw these lines below your arrow, below your arrows, right? Like so. And then obviously you need one to start with. Okay, and I'll just put this one down there as well. We'll see how far those things go. Okay, and then you label. So we're drawing this table, and then we label it. So we put down initial, right? Then I'm going to put down something called R/P. This is, in other tables, this is called the change. They represented with a C, which is also okay, which means change. I'm going to put there reacted/produced. Okay, and then I'm going to put there equilibrium. Now this here, equilibrium, does not this represents the concentration. Okay, I mean not concentration, the number of moles. Okay, and then let's just pull this up. I'm going to draw a line across, because this is exactly how you set up your table, and a line across over there, a line across over here, and then finally what I'm going to do is I'm going to write a final row and call that the concentration at equilibrium, which is going to be EQ in brackets, which is equal to the number of moles at equilibrium divided by the volume. Okay, and so let's just do that over there. Okay, let's close off that table. Hopefully that's enough space. My handwriting is not too big. Okay. There are reasons I never became a graphic artist. Anyway, okay, so we're not yet done with our table. As you can see, all I'm doing is I'm just drawing out the table now. I haven't even done any calculations, and this is why I'm stressing the importance. It is of critical importance for you to set up the table correctly. You write down number 1, the equation. Number 2 is you draw the table and you put down ICE, which is initial, change, or an equilibrium, or initial, reacted / produced, and then equilibrium. And this final row over here is meant actually just for calculations. The first 3 rows, this over here, must be in moles. Okay, that is in moles. Okay, and then finally the last thing that you need to do is you need to draw stars. Now please don't argue with me, you must just draw the stars. Okay, and I'll tell you what the stars are about when we get there. Okay, and now you start filling in information based on the question. The other thing here to note is that the volume is 1 cubic decimeter. Oh, let's not write that down, let's just circle it. Okay, when 0.496 moles of H2 and 0.181 moles of I2 are heated in a container, the equilibrium mixture is found to contain, now this question seems a bit odd because that number seems very, very small, but it's okay, we will work with it. The equilibrium mixture is found to contain 0.00749 moles of I2. Calculate the equilibrium constant for the reaction at 450 degrees Celsius. They must give you the temperature because the temperature will affect the Kc value, and we'll speak about that in the next video. Now we've just filled in everything that we got, right? Initially, when we started this reaction, we had 0.496 moles of H2, and we had 0.181 moles of I2, and this was heated in, now they don't say we had any hydrogen iodide in the system, which means we started off with 0. Okay, now they tell us when the system reaches equilibrium, that means you go to your equilibrium column, and you can see that there's 0.00749, 0.00749 moles of I2 in the system. Okay, and that's all that we've been given so far. Now for you to fill this in, you'll get some marks. And by the way, this is worth 9 marks in an examination. That is roughly 6%, I think. Yeah, 6% of a matric final examination. So now we've just filled in all of that. The next step is to do the following. Okay, so step 1 was write out the reaction. Step 2 is set up your table correctly. Step 3 is fill in all the given information. Now at the 4th stage, all we're going to do now is we're going to start using the information that has been given. And what you now need to do is you need to what I call examine the change. You need to see what happened. You started with 0.181, you now end up with 0.00749. Now my question to you is, did the iodine increase or decrease? To go from 0.181 to this over here, did you add or did you subtract to it? Well, I mean, you guys are smart, so okay, definitely you subtracted, so you write in a minus here. And this is when you examine the change. Now, if you find that on the reactant side, which is most of the cases, right, that we have subtracted from the reactants, then all the reactant sides must have a subtraction. They must all have a decrease. Okay? And if these things decrease, the opposite side of the arrow, you put in this column pluses. Okay, so this is all part of properly setting up your table when you're examining the change. So that's a plus. Okay. Now let's proceed further. Now we're going to come to some real calculations. All of this so far up until this point was just given in the question. 0 was practically given because you didn't start with anything. That was given, this was given. Then when you examine the change, you could tell me this was going to be minus, minus, and this thing over here is going to be plus. Okay? Now, 0.181 minus what will give me that? You can do that on your calculator. Minus 0.00749, and that gave me 0, comma, this is where we're actually doing calculations, 0, comma, 17351. Okay, now people, this is where my stars come in. What do these stars represent? Let me tell you the secret. These stars represent ratio and proportion. And what ratio? It is this ratio that you see highlighted in blue over here. 1 is to 1 is to 2. So if we take 1 egg and 1 cup of milk, and that gives us 2 cakes, then it means if we take 2 eggs, 2 cups of milk, it will give us 4 cakes. Ratio and proportion is simply just multiply and divide. You cannot say, how do you get from 1 to 1? You got to multiply or divide by 1. How do you get from 1 to 2? You got to multiply or divide. In this case, you got to multiply by 2. So that's what you need to observe. These stars will remind you in an examination that you must work with this row in ratios and proportion. So if I used 0.17351 in a ratio of 1 is to 1, then this must also be 0.17351. Where do I get this from? I get it from the fact that I put my stars here, which tells me I'm working in a ratio of 1 is to 1 is to 2. Now if 1 is to 1 is to 2, how do I get from 1 to 2? Using division or multiplication. I multiply. So I'm going to take 0.17351 and I'm going to multiply it by 2 to get what's going to go here, because 1 goes to 2 by multiplying. That goes to that by multiplying by 2. Okay? So whatever I've done in that ratio there, whatever I've done in this ratio over here, I've got to do it in this row as well. 1 goes to 1 by multiplying by 1. Okay? So let's take 0.17351 and multiply that by 2. It gives me 0.34702. Okay, now excellent. Now the rest is trivial. Now you just say 0 plus this thing over here must give me the same thing there, 34702. This thing minus this thing must give me, that's 0.496 minus 0.17351. And that's going to give me an answer of 0.32249. Now people, in the last row over here, you're going to use the volume. In this case, it was very, very easy. In the next examples, we'll probably do something a bit more challenging. So in this case, we find that it's just going to be as simple as saying it is 0.32249 divided by 1 decimeter cubed, because you take this row and you divide it by the volume, and then you get your answer for this one. So I'm just going to do the first one in full with you, 0.32249 divided by 1, which stays the same thing. This one over here is 0.00749, and this one over here is just going to be 0.34702. Why were these numbers the same? Because they work in proportion, a ratio of 1 is to 1. Why was this number doubled? Because this row works in proportion of 1 is to 2, so I had to take that and I had to double it. The rest was just saying let's subtract or let's add based on the plus and the minus signs that I have given you over here. Okay. And then in the final row, all you need to do is divide by the volume, and in this case the volume was 1. Now to calculate KCs, you're going to take the formula that you've written out here, and I'm going to do that in a black pen. You get usually between 5 and 6 marks in an examination for this table. And then finally, Kc is equal to Hi to the power of 2, its equilibrium concentration, divided by H2 times I2 in a ratio to the powers of 1. Now, this last part is 3 marks, 1 for the formula, 1 for substitution, 1 for the answer. And I'm going to say that is equal to 0.34702, because that's a product, raised to the power of 2, divided by 0, let's put I first, 0.32249 0.749, and you can see I'm not rounding off anything over here, right? Multiplied by, all of this is in the denominator. Okay, wait, let's just use another color over there so that we'll still be able to see it. Multiplied by 0.00749. Okay, and you can extend that over there. Okay, so, and then that's just equivalent. The rest is calculator work, and because let's just put that in and see what we get. That's going to give you 0.34702 raised to the power of 2 divided by 0.32249 multiplied by 0.00749. Okay, and that gives me an answer of 49,86. Okay, now you'll be happy to know that the equilibrium constant has no units, right? There are no units for the equilibrium constant. And that's because all the units will cancel out because we're working with a balanced equation. So that was the first example of how to deal with the table, how to set it up correctly. And I know it was a long example, but please rewind, replay, and hopefully we'll do another 2 with you shortly.